Most manufactured objects are designed with a set of high-level functional goals in mind. Wind turbines should be compact with high power output, bicycle components should be lightweight and sturdy, and this robot should have fast, precise locomotion with little energy consumption. These goals typically conflict. Longer turbine blades can extract more energy, but they are heavier and less compact. Some designs are strictly worse on all metrics, so they do not merit consideration. The designs that exhibit the best performance trade-offs are called Pareto optimal designs. They can be found using multi-objective optimization. Of course, these designs do not exist in a vacuum. The optimization must account for constraints and assumptions derived from the part's context or the scenario in which it will be used. For the wind turbine, we must consider the wind speed and air density at the installation site. For the bicycle rocker, we must preserve the bolt hole locations so that the part fits within the surrounding assembly. And to judge this robot's locomotion, we must account for environmental parameters like the ruggedness and friction coefficient of the terrain. The engineer is not able to control these context values, so they cannot be optimized like a typical design variable. Instead, engineers must find the appropriate Pareto front for each situation by fixing a particular context, then optimizing the design. However, engineers typically need to explore many contexts for a given part. With existing tools, engineers must rediscover each fixed context Pareto front from scratch. This process is tedious and wasteful because we cannot reuse any information that we had discovered for previous contexts. To streamline this process, we introduce a new object called the Pareto Gamut, which captures the Pareto optimal designs over a range of contexts. We develop a method to discover the Pareto Gamut directly, rather than discovering one fixed context slice at a time. Once we have discovered the Pareto Gamut, we can extract the Pareto optimal designs corresponding to any fixed context. In traditional fixed context optimization, the design parameters form a design space. Each design is then mapped into the performance space. The set of designs that have optimal trade-offs between the metrics are called the Pareto set. The image of these designs in performance space is the Pareto front. These Pareto designs correspond to a single fixed context, Z. However, it's common to explore multiple contexts within a given range. To organize these fixed context fronts, imagine stacking them along an additional axis according to their context value. By collecting the fronts at many distinct contexts, we get a clear picture of how the Pareto front changes as the context varies. This collection of Pareto fronts forms a single object, which we call the Pareto Gamut. To efficiently uncover this gamut, we devise an algorithm that samples design points from many distinct contexts, then optimizes each point within its fixed context. We use these optimal points to compute a first-order approximation of the Pareto Gamut, which exposes a neighborhood of optimal points not only in the original fixed context, but in other nearby contexts as well. By discovering entire patches of the gamut and sharing information across contexts, our algorithm amortizes the cost of optimization across the whole range of context values, making thorough exploration possible. Our wind turbine is optimized for mass and power output under various wind speeds. Because wind is dynamic, engineers must evaluate each candidate design under many contexts, as shown by the sampled curve. By visualizing the query design's performance next to the Pareto Gamut, an engineer can visually inspect its strengths, where it's close to the Pareto Gamut, and its weaknesses, where it diverges, relative to the achievable optima in each context. We quantify this relative optimality in the lower right plot. By exposing each design's sensitivity, we help engineers avoid designs which are overly optimized for some context, but poorly performant in many other plausible situations. By studying part of this bicycle suspension system, we show how the Pareto Gamut might be used for hierarchical design. The shared pivot positions provide a context for each adjacent part. The pivots impact each component's optimal designs and their achievable performance, but pivot locations are typically fixed in advance. This is because pivot location primarily impacts the bike's suspension characteristics, such as the anti-squat shown here. Desirable suspension behavior is personal for each rider, so it cannot be universally optimized. Engineers must explore different pivot locations for different circumstances. Strong pivot locations must yield the desired suspension characteristics, while also admitting sufficiently aesthetic and high-performing designs for each adjacent component. By providing immediate access to the high-level characteristics and the optimal part designs in each pivot configuration, our Pareto Gamut naturally facilitates this exploration, which was difficult before. Solar roof design is challenging because architects must balance quantifiable metrics like solar output against subjective metrics like the aesthetics of the house and its relative positioning. The Pareto Gamut allows us to treat the subjective decisions as a context, while optimizing the quantifiable metrics over several possible scenarios. In particular, we optimize the roof for power output in the morning and the evening over a context that modifies the global orientation of the building. Even with a large design space, our algorithm identifies designs that are consistently oriented toward different points of the sun's trajectory, regardless of the building's orientation. Architects can then peruse this collection of functionally optimal designs to select the best option for a given aesthetic goal or environment. Thank you for your attention.